Hello and welcome back to Geometry. We're in Chapter 8, Section 1. We're talking about similar polygons today. Okay, here we have a couple of trapezoids and the bases here, the measures of these bases. If we compare those, 6 and 4, if I was to compare those using fraction 6 compared to 4, I can simplify that down to 3 to 2. Now if I take a couple of other corresponding sides, like this side right here and this leg, 9 to 6 also simplifies down to 3 to 2. So how this side goes to that one is the same as this one to this one. Okay, now here's another interesting thing. If I take two sides within the shape, like 9 and 12, so I compare 9 to 12 like that, that can be simplified down to divide both of them by 3, 3 to 4. This, 4, there we go. And now take corresponding sides over here, 6 and 8. That can be simplified down also to 3 to 4. So the sides within a shape towards each other also have the same ratio as the sides within a shape that's similar. Okay, so I could use this information or I can use this information right here. Pretty cool stuff with similar polygons. Alright, so corresponding parts in polygons, the angles, corresponding angles are the same, and corresponding sides form a ratio. Okay, so corresponding angles are congruent and the side lengths form ratios that are equal. And now the scale factor, what we looked at here in the previous one, the scale factor from one to the next. Let's say this is the original, this is the new, so my scale factor here to make a transformation from this to this would be 4 to 6. So the scale factor that would get me from the blue shape to the green shape would be 2/3. If I multiply any of these sides by 2/3, I get the new one. So the scale factor is new to original, same as the ratio of the lengths. You just simplify the ratio of the lengths. All right, so we want to find a corresponding length here. The way I like to set this up is if they are the same way up and have corresponding sides in the same place, I can just make a fraction like that. So now I have x over 20 is equal to 30 over 24. Now you could cross multiply here, and we're going to do that for a moment. Show you what happens. If we cross multiply, I get 24x is equal to 20 times 30. All right, I multiplied 24 over here and 20 over there. Now in order to solve for that x, I have to divide both sides by 24. Notice that 24 is back where it started. So if you can set it up to where the x is on top of a fraction rather than on the bottom, all you have to do is take that denominator and move it to the numerator of the other side. So now we can simplify this. 20 times 30 is 600 divided by 24 is 25. You could always check to see is that correct by setting up the ratios, say 20 to 24, is that the same as 25 to 30? Alright, and here we want to find a corresponding length in the diagram. Triangle TPR is similar, this sign right here, the little wave means similar to triangle KPZ. Oh, sorry. Haha. It's XPZ. There it is. XPZ. And we want to find the length of the altitude PS. Okay, the altitude goes from the vertex in a right angle to the base. So this is what we're looking for. I'll call that X. Alright, and so now I have my little fraction set up. Alright, X to 6. X to 6 is equal to, and here's my fraction, 20 to 8. 20 to 8. Now I'm going to use my super trick that I just showed you. Take the 6, move that up here. That's multiplying by the denominator on both sides. Equals 20 times 6 divided by 8. That's 120 divided by 8 is 15. So this altitude right here is 15. Just like that. There you go. Now, the book will show you a slightly different method. They went ahead and found the scale factor between the two, and then they multiplied this side by the scale factor. That's another way of doing it, but whichever way works best for you, pick your favorite. All right, Theorem 8.1, perimeters of similar polygons. Just like the sides of similar polygons have a corresponding ratios, the perimeter does too. So if you take the perimeter of the new shape over the perimeter of the old, that's the same as taking a side length. Same scale factor right there. So here we have a pool. An Olympic-sized pool is 50 by 25 meters. And they're building a new pool that's going to be similar, keyword right here, similar in shape to an Olympic pool, but will have a length of 40 meters. All right, so it's going to be a bit smaller. This is going to be 40 meters. Okay, now they are saying find the perimeters of an Olympic pool and the new pool. Okay, so you could find the perimeter of this and then make a ratio with the other perimeter, or we could use my super trick and say make a couple fractions. 25 over 50 is equal to x over 40. Find the side length first, and then find the perimeter. There we go. Super trick right here. Put the 40 over up on top. Whoop. Equals x. And then simplify. 25 and 50 can be simplified. Boom. I got 2 here, 1 there. 40 and 2 can be simplified. Boom. I got 20. So x equals 20. All right. So that's 20. Now find the perimeters of an Olympic pool and the new pool. Perimeter here, 50 plus 50 plus 25. Add all of these together to get the perimeter. Boom, plus, plus, plus. 50 plus 50 is 100. 25 plus 25 is 150 for this pool. Here we have 40, and there we have 20. 20 and 20 is 40. 40 plus 40 is 80, plus 20 is 100, plus 40 is 120. There we go. All right. Now, if you take the areas of shapes, okay, let's find the areas of these first. The area of this one, length times width, 3 times 5 is 15. The area of this one, 9 times 15 is 135. All right, let's see how those correspond to the side lengths. We have 3 here and 9 there. Well, to get from 3 to 9, I had to multiply times 3. Okay, so the scale factor is 3. Now, 15 times 3 is not 135. So what is the possible scale factor between 15 and 135? Well, 15 times 9 is 135. So how do we get from 3 to 9? Well, 3 squared is 9. And area, remember the units for area are always squared. So if this is centimeters, that would be centimeters squared, while this is just centimeters. So area is squared. So we would take the scale factor and square it. That would give us the ratio of the areas. All right, so Theorem 8.2, the areas of similar polygons, their area, the ratio of the areas, is equal to the squares of the ratio of the corresponding side lengths. Sounds complicated, but it's basically what we just did. So if I have an example here, I know that triangle ABC, the area is 36, okay, and these corresponding sides are 10 and 5. So if I have, if I want to find the new area of DEF, I would take 10, right? And 5. The ratio of the areas is the same as this squared, is equal to ratio large triangle, 36, over small triangle. Okay, I set myself up the wrong way around here, so I'm going to have to do 2 steps, but that's okay. So I have 100 there, and 5 squared is 25, is equal to 36 over x. All right, so I'm going to have to flip this around. This goes up here, this goes up here, and the 100's going to come down here. But I'm not going to do that in one step for you because I'll confuse you. So here we go. 100x is 36 times 25. And now we're going to divide by 100. Boom. I'm going to simplify a little bit. 25 goes into 100 4 times. 1. And 4 goes into 36. Simplify these two. 4 goes into 36 9 times, so x is equal to 9. And if I want to go back and check that, remember from 5 to 10, what did I have to do? I had to do times 2. So if I want to find what I have to do with the area from here to there, I'd have to do 2 squared, which is 4. So if this is 9 times 4, that gives me 36. Cha-ching! Correct. Very nice. All right, now we're supposed to determine whether they are similar. Okay, well, we know for similar polygons that corresponding angles are congruent, and we know that corresponding sides have an equivalent ratio. So we're going to start, and I'm going to put the new shape on top so we can practice just like scale factor new shape. I'll say this is the initial, this is the new. All right, we'll read left to right. So new shape on top. So I'm going to do 8 over 12. Let's see whether that's equal to. It's equal to. Let me just write out all these 6 and 4. And then the others are also 6 and 4. Corresponding sides seem to have equal measures. All right, 6, 4. Okay, 6 looks like it corresponds to 9. And same thing here. So 6 over 9 and 4 to 6. All right. Let's see, are these equivalent ratios? You could cross multiply to find that, or you could simplify. 8 over 12 would simplify to 2 over 3. 6 over 9 simplifies to 2 over 3. And 4 over 6 simplifies to 2 over 3. So their ratios are all the same. Very good. Check that. Now let's check the angles. Well, we can see angle A is congruent to angle K. All right, but we don't know about the others. We don't have information. And if we look at this, if I take a line right there, horizontal line, and check that, notice from E, this line goes up over here. And from P, that line goes down, which means this angle is definitely not congruent to that one. And therefore, these are not similar because their angles are not, corresponding angles are not congruent. These two are not congruent. All right, and that's all we have for this lesson. Remember, scale factor is new to original, which is the same as the ratio of the lengths.